In this video, we work our third example of implicit differentiation, or of an implicit differentiation problem. The curve is given by x to the 2/3 plus y to the 2/3 equals 5, and we get to see this really pretty shape. I wanted to show you what the graph looked like before we got started. I would have you notice that there are two functions here. We've got this top function and then the bottom function. The top function is where y goes from 0 to this value, which is, well, when x equals 0, we get x, y is equal to 5 to the 2/3. So it looks like that. And then the bottom half of the function is where y goes from the opposite of that value to 0. And so we have that. So it's a very pretty graph. But we've got a function that's well defined at each of these pieces. The derivative is undefined here at 0 and 0, at x equals 0 on either graph. And then the tangent line, of course, is undefined at these little corners on the right and left as well. I mean, we could probably find the tangent line from the top graph and then the tangent line for the bottom graph. But yeah, I guess it looks like the slope is approaching, it's like sort of small and positive here, and then like small and negative here, but I think it's actually going to 0, kind of smoothing out. All right, so that's our graph. Let's use implicit differentiation to find the derivative now. So we're assuming that y is a function of x. So we're either on the top half or the bottom half of that graph. And then we differentiate both sides with respect to x under that assumption. The derivative of x to the 2/3 is just 2/3 times x to the 1 less power. 2/3 minus 1 is negative 1/3. The derivative of y to the 2/3 requires the chain rule because we're differentiating with respect to x, and y is a function of x. So we're going to have 2/3 times the inside function to the 1 less power. 2/3 minus 1 is 2/3 minus 3/3, which is negative 1/3. And then we substitute in our y. Remember that y is a function of x. And then multiply by the derivative of the inside by the chain rule. And that equals the derivative of the right-hand side, which is 0. And we're trying to get dy dx by itself. So we'll subtract this term from both sides and then divide by this one. So we'll have dy dx equals negative 2/3 x to the negative 1/3 divided by 2/3 y to the negative 1/3, and the 2/3 reduce. And using exponent properties, this x to the negative 1/3 would become an x to the positive 1/3 if we put it in the denominator, because if you have x to a negative power, that's 1 over x to the same power but positive. And we would also flip the signs on this one. If I've got this y to the negative 1/3 in the denominator, that would become a y to the positive 1/3 if I put it in the numerator. So just using negative 1/3 for our n value here, I get that. Then when I multiply them together, I get negative y to the 1/3 over x to the 1/3, or y divided by x to the 1/3. So we can see that dy dx is undefined when x equals 0, which is consistent with that picture that we see. That's what our graph looks like at x equals 0, right? On both graphs, both the top function and the bottom function. And then the y values have opposite signs. And this is a formula for the slope at any point xy that satisfies the equation. We might substitute in a particular value of x. I think I substituted in x equals 2. When x is equal to 2, my y value, did I use x equals 2 or x equals 1? Not sure. Hold on just a second. When x is equal to 2, we get y to the 2/3 equals 5 minus 2 to the 2/3. So y would equal 5 minus 2 to the 2/3 raised to the 3/2 power. Because you're just taking both sides and raising it to the 3/2. So we're gonna have like a point essentially right there. That's one point on the curve. And then because of symmetry, we'll have the opposite x value and the same y value. Should be on the same horizontal line. And then because of symmetry, we're going to have the same or the opposite y values and the same x values as well. So I'll just multiply that y value by -1. I know these expressions look really complicated. Would have been better to choose x equals 1 rather than x equals 2. But these 4 points are on our graph. Let's use x equals 1 as well. When x is equal to 1, we've got a 1 to the 2/3, which is 1, plus y to the 2/3 equals 5. So y to the 2/3 equals 4. And then we'll raise both sides to the 3/2 power. So that is the square root of 4 cubed, or you can do square root of 4 cubed. Either way is fine. So y is equal to 8. So x equals 1, y equals 8 is on the graph. And then due to symmetry, we'll have x equals -1, y equals 8. And then you could have the same x values on the bottom part, x equals ±1 and y equals -8. So all of these points are on the graph. These are much nicer to work with than these. But for some reason, I chose x equals 2 last night. I don't know why. But let's look at the tangent line, or let's look at the graph at each of these points, and then graph the corresponding tangent line, and we can do the same thing with these points as well. So those are the points that I mentioned. That's the exact answer. But then I had Desmos label the points, and so we can see the decimal approximation on the graph, which is really nice. And then we can find the tangent line in all of these quadrants for all of these different points. I think I probably chose x equals 2 as opposed to x equals 1 because it's a little bit farther than from the y-axis to make a different, a sort of more, a less steep tangent line. Now our slope was negative y divided by x to the 1/3 power. So I just copied and pasted my y value, and then I copied and pasted my x value. There's my y divided by x to the 1/3. Actually, I put that point in there twice. And then I graph the tangent line, y is equal to the y value plus the slope times x minus the x value. And similarly, for our slope, we have y over x, and then we substitute in the appropriate value for y and the appropriate value for x. We get that. There's something not quite right about it. The x value here should have been replaced by -2, but then you square it anyway before you take the cube root, so it doesn't change anything. Still tangent to the curve. Still turns out to be the same y value. And then we, yeah, that was y equals the original y value plus the slope times x minus -2, which is the same as x plus 2. Quadrant 3, we've got this point. Then we have y, the slope is negative y over x. This y value is negative, this x value is negative, the negatives reduce. And you get this as your slope. And we graph the tangent line as usual. Kind of reminds me of Argyle socks, right? And then in quadrant 4, the x value is positive, the y value is negative. And so this negative y over x raised to the 1/3 is this number. That's our slope this time. And so we get that. And everything looks a lot simpler if we're substituting x equals 1 and y equals 8. But yeah, I guess we could do that. That's the idea. So let's look at x equals 1, y equals 8 as well. At that point, and the slope, I'm just going to say 1 star. Oh, no, it won't let me do that. I said that was slope 4. I'll call this slope 5. Is y, or the slope is equal to negative y divided by x, which is just 8 divided by 1, which is 8, raised to the 1/3 power. So the slope is -2. And y is equal to the original y value plus the slope, which is -2, times x minus the x value. And we get a tangent line there. That's another point in quadrant 1. There's another one. And then because of symmetry, we could have in quadrant 2, x equals -1, y equals 8. So our slope, instead of being -2, it should be +2. Because the slope is -1 divided by, or -1 times 8 divided by -1, the y divided by the x, which gives us -8. And then we raise it to the 1/3 power. So we get a +2 that time. And then y equals the original y value plus, what is it? The slope times x minus -1, which is x plus 1. And we get that line. And you might be saying, oh gosh, this is kind of tedious. You have to find particular values and then you have to plug them in. Isn't there a simpler way? Well, we could just solve for y in the original equation and find the equation for the tangent line that way. So let's do that on our paper. So we know that x to the 2/3 plus y to the 2/3 equals 5. If I want to get y by itself, I just subtract x to the 2/3 from both sides. And then to get rid of the 2/3 power, I want that exponent on the y to be 1. So I raise this to the reciprocal power. So just take that fraction and flip it. That's going to be my exponent on each side. So that's what y is as a function of x. I feel like that's only going to give you positive values for y though, because with the square root, there's something not quite right about it. So we cube both sides. Yes, well, let's think of that differently. So let's do that. Sorry, I'm thinking to myself. In order to get rid of that third in the denominator, we're going to cube both sides. So that would make that this expression cubed equals y squared on the right-hand side, or excuse me, on the left-hand side. So y squared equals this number. And then if we take the square root we should add a plus or minus. So now we have positive and negative values for y. So our slope, which was initially negative y divided by x to the 1/3 power, is going to be negative plus or minus 5 minus x to the 2/3 raised to the 3/2 power, all divided by x. And that's our function of x for the slope. So I think if we use this as the equation for the slope at a particular value x naught, we should be able to make a slider on Desmos.com and vary x using the slider and then draw the tangent line. Let's see if that actually works. So we can solve for y explicitly. And again, we have that top function and bottom function, which are opposites of each other. There's the top function, there's the bottom function. I'm using f at the top and then g at the bottom. And then we've computed y prime as negative y divided by x raised to the 1/3. And for the top function, I'm just substituting this in for y. So that gives me the graph of the derivative. So you can look at that graph and it seems consistent with our intuition. If we draw a bunch of tangent lines on this side, all the tangent lines are going to have positive slope and the derivative has positive values. Over here, if we draw the tangent lines, they're all going to have negative slope and the derivative has negative values. So it is what we would expect. What's nice about this, when you can get y by itself, is that you can sketch those points on the curve and label them, and then you can use the sliders on Desmos.com to vary the points. So that's nice. I've plotted the point, I've plotted the derivative value at that point, and we can label it so that we can see what the derivative is there. And then we can graph the tangent line as well at that location. And then just vary your x's using the slider. Again, that's the problem with these relations. Most of the time, we can't get y by itself, which is the reason why we're using implicit differentiation in the first place. But in this case, we were able to get y by itself, so we can see what the tangent lines look like on either side. And we can see that as we approach 0 from the left, that line is getting a much larger and larger and larger slope. And then as it switches sides, and the slope becomes very large and negative. So we're sort of on this branch of the derivative graph here. So that's kind of cool to be able to see that. And then we can do the same thing with the other function, the bottom function. We can look at that. Then the derivative for the bottom is going to be very similar to the derivative for the top. We just multiply the y value by -1. And then rather than using these points, I'll graph x naught and g of x naught and label it. And then we'll graph x naught and that derivative for the bottom function at x naught and label it. I like the points to match the corresponding function. So I will use the screen here and then there. We don't need that one labeled now. We don't need that one. We'll let y equal g of x naught plus the slope there times x minus x naught. And I like to make that a dotted line. And then we can move the sliders again and we can see everything going from location to location. This is a good way also to talk about the second derivative. as well as the first derivative. So you might think, okay, well, how is my slope changing? Well, if we want to think about how our slope is changing, we can take the derivative of the first derivative, and the first derivative looks like this. For the bottom function, it's this purple graph. As we go from point to point, on the interval from 0 to 5 to the, what is that? 5 to the 3 halves, which is about 11. That slope is decreasing. The slope is decreasing. Then the second derivative is going to be negative. And if the slope is increasing, then the second derivative is positive. But if we look at the slope here, these slopes are going from 0 toward negative infinity. So the slopes are getting smaller and smaller and smaller. And then on this side, the slopes are, it looks like the slopes are increasing. All those slopes are positive value, but they're actually getting less steep. So it goes from a very large positive slope to a smaller positive slope. So the slope is decreasing here, and then it's also decreasing on that branch as well. Since the slopes are decreasing, we say that the graph is concave down. Now, if we get rid of this, we look at this original green curve, we say that it's concave down. It kind of looks like a cup facing down. That's going to be true at any time that this slope is decreasing. So the derivative is decreasing. That means the second derivative is negative when the graph looks kind of like this. And you might just see like one half, the left half or the right half. That's kind of like the right half of something that looks like that, and that's the left half, and they've just been joined together like this. But this is concave down and this is concave down. And then if we want, we can go back to that top half of the graph. So my notebook's got like bottom functions and top function stuff everywhere. There we go. Here, if we look at the tangent lines on this part of the graph, the slope goes from 0 to increase or to positive, and then the slope gets more and more positive, increasingly positive, as the line gets steeper and steeper. And we can see that if we just look at the values of the derivative, those values on the derivative graph are actually increasing as well. So when you see that, you know that the second derivative is positive. Then if we go from this left half to the right half, we see the slope is very large and negative, but then it gets less negative and less negative and less negative, and then it approaches 0. So the slope is still increasing over here, even though the slope is initially negative. So in that case, when the graph looks like that, we call it concave up. This is concave up, and this is concave up. Normally, we would say it just looks like a cup facing up, but it's like we've taken this cup and sort of, again, changed it. Like we've split it like this. So you've got one half that's going up, and then one half that's going up. But this is concave upward, and this is concave upward. And it's because the derivative is actually increasing as you go from left to right. Like if you look at the y values in the graph, they go up. If you look at the y values in the graph, they go up, even though the y values are negative on this side and the y values are positive on this side when you're talking about the derivative graph. So in those cases, again, we're going to say that since the derivative is increasing, the graph is concave up, and that means the second derivative should be positive. And then on the bottom half of the graph, it's concave down on both of those pieces. And the second derivative should be negative. So let's compute the second derivative using implicit differentiation and see if we actually get negative values for that. Now you have options for how you compute the second derivative. You can do so in terms of x by differentiating this again with respect to x. Or you can differentiate this expression with respect to y. Or not with respect to I, with respect to x using implicit differentiation. Let's do that. So we've got the derivative with respect to x of dy dx. That's the derivative with respect to x of this negative expression raised to the 1/3 power. We're going to use the chain rule. The derivative of the outside function is negative 1/3 times the inside function raised to the negative, or 1/3 minus 1. 1/3 minus 1 is 1/3 minus 3/3, which is negative 2/3. We're going to have y, and then we put the inside function back inside without differentiating it. And then we take the derivative of the inside by the chain rule. Our second derivative with respect to x is negative 1/3. Now I've got a fraction raised to the negative 2/3. You can always, if you have a fraction raised to a negative power, you can flip it and make that power positive. If you're curious about why that's true, we can always talk about it. And let's do that, not in this video. And then for this, we would use the quotient rule. So I've got, this is my high function, that's my low function. I'll have low d high, the derivative of y with respect to x can just be represented by dy dx, minus high d low, derivative of x is 1 with respect to x, all divided by low x squared. And dy dx was negative 1 times y divided by x to the 1/3. And we're subtracting y from that. And then we're dividing by this x squared. So I see that the numerator has a negative factor here and here. So I can factor that negative out. That negative times this negative will make that expression positive. Having some problems with the sort of glare on the camera. Sorry about that. Sometimes if I put my fingers in the view, it like changes the colors and makes it easier to see. All right, so we have 1/3 here. This is x divided by y raised to the 2/3. And now I've got an x times y divided by x all to the 1/3 plus y all divided by x squared. I'm trying to simplify this as much as possible. Anytime you've got a quotient raised to a power, you can apply that power to the numerator and denominator separately. This is an x to the first divided by 1 times a y to the 1/3 divided by x to the 1/3. We're adding y, dividing by x squared. And then this 1 divided by x to the 1/3 is going to give me an x to the 2/3. We've got x to the 2/3, y to the 1/3 plus y, all divided by x squared. And I guess we could factor out a y to be, yeah, I don't know. Should we factor out a y to the 1/3? I don't know. I think I'll distribute the x to the 2/3. X to the 2/3 times x to the 2/3 is x to the 4/3 because you just add the exponents. I'm distributing that there and there. And I'm taking all of that and dividing by this x squared times y to the 2/3. Like, this is really tedious, I know. It's kind of annoying, actually. But I'd like to simplify this as much as possible. I know that these guys have a y to the 1/3 in common, so I can factor out a y to the 1/3. And these guys have an x to the 2/3 in common. We got x to the 2/3 divided by x squared from the denominator. And then I've got a y to the 1/3 divided by y to the 2/3 from the denominator. And then I say, okay, well, what do I have left? X to the 2/3 times y to the 2/3 times x to the 2/3 would be my numerator. Or that term in the numerator. And this times a y to the 2/3 be what I have right there. And actually, x to the 2/3 plus y to the 2/3 is 5, because that was the way our function was defined, or our relation was defined. So we end up with 5/3, and then this divided by this, that's 2/3 minus 2, which is 6/3. So it's going to be x to the negative 4/3. And 1/3 minus 2/3 is y to the negative 1/3. And so we end up with 5 divided by 3 times x to the 4/3 times y to the 1/3. Like, okay, that was a lot. Well, that's our second derivative. So when y is positive, and x is positive, well, x to the 4/3 is always going to be positive, no matter what x is, because what this is saying is take x cube, or raise it to the 4th power, which is always going to be a positive number, and then take the cube root, so it's still positive. Y to the 1/3 is going to be positive when y is positive, and negative when y is negative, because the cube root can be positive or negative, and you're raising y to the 1st. So when y is positive, and the second derivative is positive. When we say the second derivative is positive, when the graph roughly looks like that, we say that it's concave up. And when y is negative, our second derivative is negative, which means the graph is roughly going to look like that, which is concave down. Oops. Now our graph doesn't look exactly like that, because it actually took like 2 pieces like that and it split them. Here the slopes are decreasing, or excuse me, the slopes are increasing and the slopes are increasing. But we could have just as easily taken those 2 pieces and then just changed the order so they look like that. And similarly, we could change the order on those pieces so it looks like that. But this is concave up and this is concave up, and that's concave down and that's concave down, because the slopes are decreasing here, which means the second derivative is negative, and the slopes are increasing here, which means the second derivative is positive. Okay, I hope that makes sense.